Hey everybody, today we're doing the differential equation problems, and today we're using what is called the Cauchy-Euler method. And the Cauchy-Euler method is a method that helps us to reduce the power of a variable if we have in front of the derivatives, right? So that is one of the methods that we actually learn to solve differential equations when you have a variable in front of the derivative. And the formula is a very long formula, right? However, it looks complicated, but when we use the method, all right, it's not too bad. The formula is a sub n times x to the n times the derivative to the n power times y divided by the derivative times x to the n power plus a sub n minus 1 times x to the n minus 1 times the derivative to the n power minus 1 divided by the derivative of x to the n minus 1 plus all this continued plus, right? A sub 1 times x times the derivative of times dy dx, right? Plus a sub 0 times y equal g of x. So in this case, right, so actually I'm missing a y, to have a y right here. Alright, so that is the complete formula for that, right? So if you have this book, you can actually look this formula. It's on page 162 in this book, okay? Our first course in differential equations with modeling application, 10th edition by Dennis Seal. That is the author, right, of this book. But again, we are going to focus more on the process of this method. And over here, you got 3 cases, right? I got a case 1, we have a distant real roots, right? Case 2, I have a repeated real roots. Case 3, I got a conjugate complex roots, right? So case 1, right? Case 1, when m equaled m1 cannot equal m2. That's case 1, right? We have a distant root. And when we have a case 1, right, the solution should be written as y equal c1 times x to the m1 plus c2 times x to the m2, right? And when we have a case 2, we have repeated real roots, right? Which means that we have the same root, right? So in this case, m1 is equal m2, right? So when m1 equal m2, then the solution of the differential equation should be y equals c1 times x to the n, m, right, plus c2 times x to the m times ln of x, right? The only difference, right, it should be m1, it should be m2, right? But the only difference between case 1 and case 2 is that we add an ln of x in front of c2, right? In front of x to the m2, we add ln of x, right? So that is case 2. Case 3, we got case 3, we have a conjugate roots, right? So it's conjugate complex roots, right? So then case 3, we got m1 equal alpha plus I beta, and m2 is equal to alpha minus I beta, right? So where alpha and beta cannot, it is greater than 0. Again, when alpha and beta is greater than 0, right? So the solution for this one is y equals C1 times x to the alpha I beta plus C2 times x to the alpha minus I beta, right? Now, we're going to use this method to solve differential equation, right? So I'm going to erase this formula because I need some room, right? And we are going to do number. We're going to do number 5. Okay, let's do number 5. All right. So number 5 in this book I got. Number 5, I got x squared y double prime plus x y prime plus 4y equal 0, right? So that is the differential equation, right? So now notice that my goal is to get rid of these powers, right? So I am going to let y, right? Y is equal to x to the m, right? Y is equal to x to the m, right? So if I take the derivative of this, I get dy dx is equal to m times x to the m, dy dx is equal to m times x to the m minus 1, right? That's the first derivative, right? The second derivative, right? The second derivative, this piece comes to the front, and I'm going to get the second derivative, right? So it's going to be the second derivative, right? That power right here means that I'm taking the second derivative, right? Over d times x squared, right? So that's the second derivative. Now this exponents come to the front, so I get m minus 1, right, times m times x to the m minus 2, right? So that's the second derivative, right? So if I simplify this, I can distribute that m inside, and I get m squared minus m, right, times x to the m minus 2 times x to the m minus 2. Yes, right? So now that I have this, okay, I took the first derivative, right? The first derivative and the second derivative, I can go ahead and substitute in this equation, right? So when I substitute that in this equation, I'm going to notice that this double prime, right, is the second derivative, right? And this y prime right here is the first derivative. So for the y double prime, I'm going to substitute the second derivative, and for the y prime, I'm going to substitute the first derivative, right? And of course, over here that I have a 4y, I'm going to substitute x to the m, because that was that is what y equal at the beginning with, right? So I'm going to substitute, and I'm going to get x squared times m squared minus m, right, times x to the m minus 2 plus y plus the first derivative, right? The first derivative is going to be m x to the m minus 1, right? I have an x over here, so it's x to the times x, right? X to the n, x times m times x to the m minus 1, right? Plus 4 times x to the m equal 0, right? So notice that now I have this, right? And I can actually cancel some powers. Notice that this x right here, I technically have x to the 1, right? So this power with this power, they go away, right? And this power with this power, they go away, right? So, and I get x to the 0 times m squared minus 1 minus m times x to the m plus, right? Plus x to the 0 times m times x to the m plus 4 x to the m equals 0, right? Notice that I wrote this just to make it sure that this x to the 0 power is 1, this x to the 0 power is 1, so technically what I get right here is m squared minus m times x to the m plus m times x to the m plus 4 x to the m equal 0, right? So now that I have this, right, what I can do is I can factor out x to the m, right? And I forgot to tell you one thing before, that x to the m cannot equal 0, right? X to the m cannot equal 0, right? So if I factor out right here x to the m outside, I get x to the m minus, m times m squared minus m, right? Plus, you know what, let me just get rid of that parenthesis thing, okay? So I got x to the m times m squared minus m plus m plus 4. 4 equals 0, right? So notice that this m right here, this m with this m, they go away, right? And I get m squared plus 4 equals 0, right? So if I subtract 4 on both sides, I get m squared is equal to negative 4, right? If I take the square root on both sides of this, what do I get, right? If I take the square root on both sides, okay, I get m is equal to plus on minus 2i, right? Because when I take the square root of a negative number, I get a complex number, right? So, which is imaginary number. That's why I get a 2i, right? Now, notice that we are in case number 3, right? So now the solution for this differential equation is going to be y. Notice that we have case, they are not only complex number, right? The two roots they are not only complex number, but they are also a repeated root, right? So which means that I will have to add a net length in front of it, right? So it's going to be, for this one, the answer for this one is going to be y is equal to cosine, right? Cosine times 2 ln of x plus sine times 2 ln of x, right? Actually, I had to add C1 and C2 in front of it. So, solution is going to be C1 cosine of 2 ln of x plus C2 sine of 2 ln of x. That is the solution for that differential equation. So you notice that the reason why we let y equal to x to the m is because we need to get rid of those exponents in front of the derivative. See how we had this exponent right here, we have x squared in front of the second derivative, and we have x to the 1 power in front of the first derivative. So that's why we need this method. Alright, I hope this helped, and I see you in the next video.